Today, we'll see the effect of a dose applied on the 20 nanometers gate oxide thickness we saw on the previous video. We have two objectives today. First one, explain how to model the ionizing dose using ECORCE. Second one, provide a first view of the effects of an ionizing dose on a MOSFET and to see the charges that are accumulated inside the oxide and the effect on the ID of VGS characteristic. So let's go back to the MOSFET we created in the previous modeling. It was called NMOS 20 nanometers pre-rad. The name is no more significant since we will add a new modeling that will apply radiation. So I rename it. This was the ID of VGS characteristic before radiation. I do not need to create from scratch a new modeling. I just made a copy of this one and change its name. So right click, rename, and call it 30 kilorad since we will apply a 30 kilorad dose. I open it. I must firstly change the physical model. We only defined three equations in the previous modeling. So equation of Poisson, transport of electron, and transport of hole. I now also need trapping of electron and trapping of hole. If I look inside the materials, for the oxide, new parameters appears, and the two important parameters are the activation energy for electron and the activation energy for hole. The default value are correct for the modeling we want to do. We also need to define the traps that are inside the oxide. So as we did for donor and acceptors, we can create function in space functions, as many as we need. So I create a new function for electron trap. It will apply, so I will apply a 10 to the 19 by centimeters cubic defects inside the electron. They are at the position 0.3 to 0.7 micrometers for the x-axis and 0.5 to 0.7 micrometer for the y-axis. To 0.52 nanometers. This is the thickness of the oxide for the y-axis. I must also be sure these defects apply only in the gate oxide. If I do not check this, I will have defect inside the silicon also. So I select it, and I can give a name, a significant name, N-trap. I do the same thing for all traps. I create a new one, the same density. This is a typical defect densities experimentally observed inside oxides. From 0.3 to 0.7 for the x-axis, and from 0.5 to 0.52 for the y-axis. And I apply a name, P-trap, and also I must be sure it's also defined in the gate oxide. If I forgot to check this, when I will launch calculation, I will have a warning telling you do not check the material in which this function applies. Now I need to modify the stimuli. So I will no more work in stationary modeling, I work in transient modeling. Okay, we'll change those parameters later. Firstly, we must define the radiation applied. So in stimuli, I can define biases, but now, because I am in transient modeling, I can also define irradiations. So I create a new one, and we will apply a cobalt-60 radiation for a dose rate of 0.3 watt by second and a total dose of 30,000 kilowatt. All temporal parameters are automatically adjusted, so I will have an end time for this modeling of 10 to the 5 seconds. I go back to the analysis. So this analysis time must be consistent with the irradiation duration. So I apply a bit longer time analysis. I must also change the lower time step. It's too much slow. The default value is too low compared to the analysis time. Well, 1 second time will save calculation time. I can also change the biases applied. Why? We can have a higher effect with a high electric field inside the gate when applying a dose rate. So instead of a 0 volt applied on the gate, I propose to apply 5 volts. That's to say the transistor is on state. Now we are done, and we can execute the modeling. And I start the calculation. It's running. The first step is done. So now I have access to others values, and I can display the trapped hole density inside the device. At the time 0 second, of course I have nothing because the radiation is not applied. But now if I look at next step, at 9 seconds, I see that I have already trapped hole density inside my gate. And if I go to the last step, I can see I have a very significant electric charge, 10 to the 17 by centimeters cubic inside the oxide. If we look at the electron trapped density, it's much lower. We have nearly nothing inside the oxide. Why? Because as we saw previously in the material, I go back to the material, in the oxide, the activation energy of electron is 0.8 eV, while the activation energy for holes is 1.4 eV. That's to say that by thermal re-emission, we are able to free all electrons that are created inside the oxide, while holes that are trapped inside the oxide stay locked inside the oxide, so we have a net positive charge that stay in the oxide after radiation. I can also calculate the ID of VGS characteristic after applying this radiation. I go back to my device, file open, and now I will create a new simulation. So I make a copy of the old simulation of the ID of VGS characteristic before radiation. I make a copy and I rename it ID of VGS after 30 kilowatt. I open it. I will start this modeling from the end of the modeling at 30 kilowatt. But because during radiation my gate was biased at 5 volt, I must have the same starting value for this modeling. That's to say I must start it to 5 volt and then go down to 0 volt. I'm ready. I have nothing else to change. I execute my modeling, and now I can say, okay, I start from 30 kilorad. No warning occurs, everything is consistent. I execute. I can go back to the display of for the x-axis, the potential on the gate, and for the y-axis, the total current for the drain. It has finished. We have the characteristic, and I see that the VTH is now 0.31 volt. It was 0.51 volt without radiation. I can add this characteristic to the Excel file we did in the previous modeling. So file, export, here it is. And now when I will register, it will not erase the previous characteristic, it will add the new one on the Excel file. I can have a look at my Excel file. And now I have both characteristics that are displayed on the same chart. So I can change the scale and so on as needed for my report. Thank you for watching. Hope you enjoy this video.